I'm Braden Barbary, and this is the video over my lab 2, which was about projectile motion. So the purpose of this lab was to see that an object thrown throughout the air will be affected by both the drag force and the force of gravity. Here, the drag force is given by the equation negative b, which is the drag coefficient, which is the constant number, times the magnitude of velocity squared times the direction of velocity. And then the force of gravity is mass times the force times gravity on Earth, g. Tracker and glow script were both used. The balled up paper was the system, and then the Earth and air both put force on the paper, so they were both surroundings. And then in the end, the drag was found to affect the final position of the paper. So for the testing, tracker was used to observe the object's position. An individual point was placed at the center of the object for every frame, and the object was tracked in this video in the following slide, which is right here. And that's the object that was tracked, and that's just its path that it took. The coding, the tracked video was used as a goal to try and get the same model with the code. And I tried to determine a drag force that would model the same trajectory as the ball that was thrown, and by changing a few parts of a GlowScript code, I was able to create a model that represented what was found in Tracker decently accurately. Here are a few key parts of the code. The ball's mass, 0.002, is just the average mass of a piece of notebook paper, which is what we used. The initial position was just the first point in Tracker, and that gave me this vector here. The ball's velocity, I used this formula, where I did the position of the ball at the second frame minus the position of the ball at the first frame over the time of the second frame minus the time of the first frame. For the proportionality constant, I played around with a few numbers and landed on 0.003 being the most accurate one. For the time, this was just how long the tracker model was, so I did the exact same time to hopefully get a very accurate model. And for the net force, that was the force of gravity, negative g times m, and I added the force of drag, negative b, times the direction of the velocity times the magnitude of the velocity squared. And then also in the code, I created some arrows that follow the ball throughout the model, and they were placed on the ball, and the length of the arrows were proportional to the magnitude of the force, which you can see in this video here. The arrows are proportional, and then that's the trajectory that's very similar to this model that was found in Tracker. And here's the data from my 3 different models. First, the gravity only model that's given in this orange color. That's just if there was 0 drag on the piece of paper, where it would end up. And you can see it's very far from the other ones, showing that there definitely is a drag force acting on the ball. This light green one here, this is the GlowScript code with gravity and drag, and then this darker green one here is the tracker. Now, the GlowScript with gravity and drag is slightly less, and I think that's just because I wasn't able to get an accurate enough initial velocity, because the point where the ball was released from the hand was kind of tough to tell, so that's why this is lower, but the angle and the trajectory is very similar to the tracker. Now, terminal velocity, what is it? It's when the force of drag is equal to the force of gravity, drag pushing up and gravity pushing down. None of my models ever reached this because they didn't have enough time to fall, and they were still increasing velocity until they hit the ground and stopped. But to simulate this, you'd have to throw a ball off of a larger building, like off of the top of the building, and then eventually in the air, it would get to that point where the net force is 0. Now, what if the ball was thrown straight up into the air with the same speed? I found that it would take longer to hit the ground. There are a few steps here. First, I calculated the magnitude of the initial velocity, because speed is the magnitude of velocity, to get 3.9134 meters per second, and then I plugged that into my GlowScript code to give me this graph. And this right here as you see, it takes 0.74 seconds to hit the ground, and this one takes 0.7. So about a 0.04 second difference, which is not big, but the original definitely takes less time to hit the ground. In this lab, the paper ball is assumed to be perfectly spherical, which resulted in constant drag. In reality, this is not true. The drag would be changing throughout the flight path, but it would be a very small difference, so we were able to ignore it. And in conclusion, the final position of the ball was able to be found relatively accurately by using one proportionality constant for the drag force. Thank you for listening.